I'm going to be discussing now a rapidly evolving area of potential model insight that is quite outside of the AnyLogic context, but it's one which has real bearing on building these building models using these tools in coming years here. And specifically, what I'm going to be talking about is the general phenomena of state space methods, and the particular issue of the use of a technique known as convergent cross-mapping that we've been applying with some kind first alerts to it from Jeff and Joanne within our context. And we've been building tools because I believe this approach offers great potential, particularly in the big data context, for use with dynamic models. This is a technique which is quite recent in its introduction, and I'll be providing some basic understanding of it with the recognition that more complete understanding requires looking at several papers that have appeared in recent years. So my talk here begins with a reflection on nonlinearity. I've used this term a couple times during the boot camp to talk about a linear system or a nonlinear system. And there's different definitions that can be used for nonlinearity that emphasize different features of it, or different, how shall I say it, there's different components of it that can be emphasized. One way to see it is a system where the behavior of the system, such as the hazard rates of transition between states, for example, depend on the state of that system. In a linear system, you'll have transition likelihoods or flows whose values are more or less independent. The rates associated with them, the hazard rate associated with them, is independent of the system state. You have the same exact chance of becoming a smoker regardless of how many other smokers there are. But once you start having a chance of becoming a smoker that depends on the number of smokers there are, a chance of becoming infected by a disease in a way that depends how many people already have the disease, you're dealing with a nonlinear system. Okay, and when we have nonlinearity within a system, it brings up some very distinctive characteristics. It can lead to surprise behavior that is counterintuitive, surprising, and one of the practical implications is it can lead to behavior in response to interventions which are very contrary to our expectations. And it's really with nonlinear systems that the biggest need is there for simulation, because if we don't use simulation, we may go terribly awry in our attempts to make decisions in the context of those systems. And health and healthcare systems are terribly nonlinear. Hence the need, in my perspective, for modeling. Now, one thing we haven't had a chance to look at within this boot camp, it's actually very readily done, but we haven't had a chance to examine it, is we can take models and depict what's called a state space of a model. Okay? A state space of a model is a way of depicting the things we've been looking at in time series plots, but with a very different perspective. Rather than looking at data on particular variables over time, what we're instead doing is depicting kind of the current state of the model and how it evolves at the time across multiple variables. Okay, and here we can imagine each element of model state associated with an axis of the state space. So if we're dealing with say an aggregate model where we have susceptible, infected, and recovered people, which is a classic model, we might have three axes of that state space. One for number of susceptible, one for number of infected, and one for number of recovered. In a given run of that model, or realization of the system would have a trajectory in that state space, okay? It starts at a point and kind of flows forward. Time here is implicit, and for a nonlinear behavior, the model behavior can exhibit real changes across that state space. So here's a three-stalk system, susceptible, infected, recover. It's a little bit easier to depict these things for sure. Actually, not a little, a lot easier to depict them for simpler systems. So I'll do that here. So we have a number of susceptible people. Here's a flow to infective. That flow to infective exhibits nonlinearity because the chance a given susceptible will become infective is something which depends on the number of people who are infective already. It's not independent of the state of the system. It depends on that. And then there's a number of effective and a number who are temporarily immune, and then they go back to a susceptible state. Now, we can depict the state space of a system like this by plotting out over time a value in a three-dimensional space, where that three-dimensional space has one axis associated with S, the value of the stalk, one value associated with I, value of number of infectives. Maybe this is for S, this is for I, and the value up here is for this temporarily immune stalk. We can imagine it playing out over time as the number of people in each of these states changes. As the number of infected people go up, for example, the distance along this axis increases. And then as that goes on, the number of temporarily immune people rise. And so it's rising up like that. Okay? So that's a depiction of a state space of a model. And we can very readily take models that we're looking at and imagine constructing a state space. Now, the interesting thing is that a model like this in the state space, if we look at the structure of that state space, we consider its features geometrically, it tells us a lot about how simply we could characterize a system like that. Turns out, for example, this one looks quite complex, but turns out it's totally flat as viewed from a certain angle. And what that's telling us is that actually even though it's in three-dimensional space, we only need information from two stalks to depict it. The value of the other stalk could be determined by the first. And that's because these three have to sum up to the same value, the total population. The other is just we know S and I. The other one is just total population minus this. So it has, you might think it has 3 degrees of freedom, and it really only has 2 degrees of freedom. You could think of it, okay? That's what's going on here. In the state space, we will often have a so-called nominal dimension, a dimension that sort of naive dimension, but then there's a intrinsic dimension, sort of based on its shape, how much it actually uses it. And I'm actually not going to have time, given the current time, to show this. But one point to say here is that with many systems, like system dynamics models, we can actually write out equations that say, with any given point in the state space, where does the system go? If you were somehow magically put here, where would it go? Or if you were put over here, how would it be sucked in? It turns out that falls out of these equations. Okay? If you have a current value of Si and R, we could figure out what the change is to S, the change is to I, the change is to R, and we could figure out where it would go next. With a stochastic system, it's more complicated, and I'll show you some examples of things like that. Okay, a feature that's really interesting in state space is the so-called fixed points, points where the system's in balance, either actually totally in balance or it sort of moves around. These are often associated with stable areas of the system, areas towards which it gravitates. Recognizing them in state space is fairly straightforward. Where do you think a fixed point would be here? A point where the system isn't changing anymore. Anyone want to hazard a guess? It's where it's sucking it into this, and at that point it's at rest. It's being sucked in and it's stability there. And if you knock it out, one of the things the stability needs is if you were to knock it a bit, it would be sucked back to that. Back to that point. Okay. Okay. Another feature of nonlinear systems is we'll have different basins of attraction. Like if we have our model of a complex system, there may be certain parameter values where it reliably ends up in one situation. But if we can just get it far enough along, it may end up in a very different situation. So maybe it goes from a state with very high rates of obesity to a situation with very low rates. Or where pertussis is, think about vaccination rates, where pertussis is endemic and every year there's small outbreaks versus a situation where it's essentially disappeared other than people occasionally popping up who traveled overseas or what have you. Okay, so we talked about nonlinearity being associated with behavior that depends on the current state. Okay, the outcomes are, we'll talk about path dependence. The outcomes now in the future are shaped very much by the history. You think about a child exposed to traumatic events, and that shapes their trajectory later in life. This is one aspect of path dependence. Been some very interesting studies done of the tragic situation of the Dutch famine towards the end of World War II, where during a period of the tumult towards the latter part of the Second World War, children in Holland underwent great deprivations. Families had a very difficult time providing enough to eat for family members, and children suffered great malnutrition and really reduced caloric intake. And the results of that are still being seen in a big way for that cohort who went through that, particularly those who went through it at certain stages of pregnancy, when they were still in utero, and the mothers couldn't find enough to eat, enough of substance to eat. They're still seeing big effects of these. And my colleague Roland Dick and I have done some work looking historically within Saskatchewan. He's done a great deal of work looking at the impact of, for example, birth characteristics and exposure in utero and outcomes. And we have some very exciting work going on in that area, which again suggests this sort of history dependence. Okay, it's not fate, but it means you have more to overcome, right? In terms of things, and this can lead to multiple basins of attraction where you can end up getting something that ends up going the wrong way. So we could start at one point, and it will go and reach one basin of attraction. It will go into one basin of attraction, reach one steady state, and in another case, it just takes off. One of the cases I've studied a lot is in that White and Garnett, I think, in the UK, is how this can happen in situations with like STI clinics and so on, where if you have STI clinics which are well staffed, which draw in people effectively, etc., you can get an infection which ends up undergoing an outbreak, and then ends up at only a modest level of prevalence. But otherwise, you can end up in a situation where it takes off to very high levels. Or to put it a different way, actually, this is a more prescient example. You can have an infection that starts with just too many people infected. The clinic staffs are a bit overwhelmed. You can't get treatment quite as early, and it ends up spreading very rapidly to the rest of to a large group of the population. Whereas if you have enough clinic workers to keep it under control, you can end up putting it to very low levels of prevalence. Two very different outcomes based on limited resource availability can tip it one way or the other. And so much in public health, is motivated by a desire to make a real qualitative difference if possible. We know this with herd immunity and so on with infectious diseases, a very prevalent thought. But the realization is there that if we could only achieve those changes when it comes to mental health and stigma, for example, or when it comes to chronic disease, this could be a very powerful thing. So with state space, I noted earlier there's this difference between the nominal dimensionality. We saw that graph in 3 dimensions. In intrinsic dimensionality, the fact that that graph is intrinsically it's flat. It's flat. It only actually occupies 2 dimensions. We talk about the structure of the manifold, the actual occupied area of the space that's in fact occupied for the trajectories. It's a little bit like, ladies and gentlemen, I'd like from the Sachs Institute. Nice example. This is in 3-dimensional space, but we would say that intrinsically it's 2-dimensional. Even if it's bent, even if it's not totally flat, we'll say intrinsically it's 2-dimensional because it's just kind of a twisted version of something that's 2-dimensional. It's a nonlinear 2-dimensional structure, but it's intrinsically 2-dimensional, even though it's in 3 space. It's very narrow and sort of bent. Okay. Turns out that, and I have another video where I go into this in particular examples. We actually have a number of models that I can share that show intrinsic dimensionality that are far lower than you might think. And it turns out even with agent-based models, and some of the analysis I've done, there's actually fairly low dimensionality associated with it. We have huge states. In principle, each person in the model can be in one of how many states? And it can be a very large state space, very large state space. Every person in a possibly different state. But the way it evolves, because people are so coupled together, it actually occupies a much smaller fraction. So what does this have to do with this notion of convergent cross-mapping and analysis? Well, it turns out that when you have nonlinear systems where there's multiple factors involved, one is affected by the other. The number of people that are smoking, or the occurrence of smoking, ends up affecting heart disease status in that model. Behavioral motivation ends up affecting smoking, which ends up affecting heart disease status, right? Pregnancy ends up tying in with smoking status in the next generation, et cetera. We have this kind of close coupling in the evolution of one state variable. Smoking status of people is tightly coupled with the other, heart disease. Okay? This is kind of a feature of these systems. There's a famous model some of you may have heard of. It's actually featured in AnyLogic in 2 forms. It's called the predator-prey model. Has anyone heard about that? So it was first inspired by events in my area of Canada, looking at the oscillations in Hudson Bay for the Hudson Bay Company between lynxes and hares. Lynxes are these sort of feline wild cats with the cute little ears, and hares. Well, we have Arctic hares. Some of them are frequent in my front yard. And I have a weakness for feeding them carrots. And they turn white in the winter, and they try to blend in. But one of the things that they found was that there were real couplings between them. And I would invite you, since we're all here together, we know AnyLogic, let's go open up one of these models. So let's get you doing something here. So I'm going to go open up AnyLogic. Here we are. And we are going to go to an area of AnyLogic that has been little used. We did use it once before with a trauma center, and we're going to use it now. So I'd like you to go to Help and Example Models. Okay? If you do that, you will see, and hopefully a better form than you're seeing it here, a representation of the example models with the system. Okay, that isn't too much better. Here we go. Okay, ladies and gentlemen, I would like you to scroll down here. There should be an area here that it ends up saying predator prey. There it is. You see that? Predator prey?
There's 2 of them.
Yeah, there are. One of them is the agent-based, one of them is the system dynamics. Let's start with a predator prey agent-based, if we could. Okay? I I don't think we need the GIS search results. The hairs weren't being plotted out by the Hudson Bay Company using GPS tracking. Okay, ladies and gentlemen, here we have predator-prey agent base. This is a system dynamics model. It's an aggregate model. Hares and lynxes, and each hare has a certain birth rate, and it has a death rate. But its birth rate is regarded as more or less fixed. But if I were a hare, what would I be thinking about? I'd be thinking about lynxes, right? And the more lynxes that are around, the higher the chance that I'll get eaten, right? Conversely, lynx, their deaths are independent of hares. They don't get mobbed by hares and, bitten to death. But there is actually, deaths actually do depend on hare availability because they could die of starvation, but their lynx natality is shown as being more or less fixed. That's the reverse. They phrased it as the reverse in other cases. Okay, so here we're going to have a graph of number of hares and number of lynx. How do you think these will behave? If we plotted this out, what do you think you'd see in terms of hares and lynxes?
Slightly out of phase.
Okay, yeah, it's slightly out of phase is right. So here we go. We're running this. And we're seeing cycles. And this is what's seen in the real world with hares and lynx. There are these cycles associated with it. And if you go probe these assumptions, say about hare natality, if you were to bump up the reproductive potential of hares here, you'll find that there's differences that are induced by this system. Now, what I heard is slightly out of phase, and that's exactly right. And incidentally, here we'll have hares and lynxes, and you'll notice the system is growing number of hares, right? The basic deal that I'm trying to convey, though, here is that we have a situation where the number of hares and number of lynxes is coupled over time, okay? And this is the way I'm going to put it. If I know the values of hares, I know a lot, and particularly the recent values, how it's changing over time. I could tell you quite a lot about the number of lynxes around. The number of hares is rising really quickly. Let's poke at this. The number of hares is rising really quickly. Here we go. What's it telling me about the number of lynx? Can't be too many of them around. Yeah, not too many of them around. If the number of hares is going down, what's it going to tell me about the number of lynxes? Probably there's a lot of lynxes around, actually. A lot of lynxes. Ladies and gentlemen, when we have one of these, this is a coupled nonlinear system. Okay? Fancy terms. The behavior of the system, my chance if I'm a hare of dying, is not independent of the state of the system. It depends on the number of lynxes around. And same thing with lynxes. So this is a coupled nonlinear system. Let's go open the predator-prey version, which is worth looking at. Okay, so here we go. We're going to go back to our AnyLogic help here, and I am in normal way. I'm having issues sort of navigating to it. Okay, here we go. Example models, and we will scroll down. I need the help of this, and we will go to predator-prey agent-based. How might you characterize a similar level of the system, but in an agent-based way? What do you think you might have? Well, agent-based is distinguished by what? An individual model of each agent. And here you might have individual agents circulating in space, right? So here we're going to have hares and lynx, and their life cycles will be very simple. A hare life cycle is particularly simple. A lynx life cycle is slightly more complicated. They go hunting, and if they're unsuccessful, they die. For a hare, it's a more bald matter. of survival. They die because of old age, or they die because of links. and they die, and then they have babies in the meantime. Okay? Okay, so here we go. So we're gonna run this model, and we're going to see an interaction of hairs and links. Here's a bunch of hairs, these green ones, and I doubt that's what they look like in Russia, but that was the color chosen. Okay. Well, a nice run of it, killed by an ugly fact. Okay, ladies and gentlemen, here we have lynxes and hairs, and you'll notice that there's also a graph of the number of hairs and lynxes, and you will notice that while there are stochastics around these points and so on, there are oscillations. And if you were to play with it, I think I'm handicapped by PLE here, but I believe that you are not so handicapped. So you could actually examine this more, but you'll notice that there are, again, cycles of sort, and they're not quite as deterministic. They're not as precise, but they are significant for many ranges of parameters. Once again here, there's coupling between it. The number of hairs depends a lot on the number of lynxes and vice versa. Okay, so let's continue to sort of follow this thread of thought. So what this is saying is that a given variable within this sort of system is entangled with other variables, okay? So the number of lynxes is entangled with the number of hairs, and vice versa. It depends a lot. It encodes information about the other. Think about it that way, informationally. The number of hairs right now in its recent history tells me a lot about the number of lynxes. It encodes that information. Perhaps even so much so that I can reconstruct it. And it turns out that we could demonstrate that quite formally. And I won't go into this, but basically this is a differential equation-based view of it, where this is the rate of change of the number of hairs, rate of change of the number of lynxes. And it turns out that if I have access to x, the number of lynxes, to its rate of change and to the number right now, I can actually solve for y. I can actually extract from it. I can extract out the number of lynxes over time, what it must be. So if I only observe hairs, this is the thing. Lynxes are harder to catch than hairs. And if I only observe the number of hairs, I can infer quite reliably the number of lynxes out there. I can reconstruct that from that single time series. I can reconstruct from a single time series information about the other hidden parts of the system. So it turns out that in work done in the 70s, I think maybe late 60s, in the 70s, in the Santa Cruz Collective and by a gentleman, a mathematician known as Floris Takens, a mathematician from Holland, in fact. What he showed is a remarkable thing. It's an utterly remarkable thing. It's so remarkable that people sometimes don't believe it until they look into it more. If we have one measurement from a highly coupled nonlinear system, I include in there health, or healthcare system, we can reconstruct the state space of the system as a whole. There's enough information in there to allow us to provide us with the information about other aspects of state of the system, okay? So given some set of observations, the reconstruction involves reconstruction of the state space, of the underlying state dynamic of the system that shows that dynamic. Those trajectories can be made from doing what's called creating an embedding from this one time series. So one time series with enough data points, and it turns out the number is not that large. People have done this sort of stuff I'll be showing with dozens of data points. you can actually reconstruct very nicely. And how do you do this? How do you create this embedded space? How do we create a kind of reconstruction of the state space? Well, the basic idea is you have one time series. You only have got one time series. And you basically take the current value of the time series tau time units ago, 2 tau time units ago, n time units ago, and you create a vector of those things. Okay? So maybe it's a 2 vector, maybe it's a thing with 2 coordinates. The current value and the last value. Or it's the current value and the value 2 times ago, for example, would be with different values of tau. And you create a bunch of these things from this single time series. This sounds like a strange thing to do. One of the places that this got invented empirically was there was a set of physicists in Santa Cruz in California, and they, of all things, they decided that they had a water tap in their research room that was used. I think it may have been in an old hospital or something that doctors used to wash in it, and it would drip. So they recorded the time of each drip, in fact, the time between drips. And they plotted it out. All they had was this one time series, so they decided, well, we create sort of these vectors of the current point, previous point, and the previous point. And they created a plot of this, and they saw a really interesting structure. What looked like random data had a really interesting structure behind it. There was some hidden order there. It was really interesting. And Flores-Takens ended up showing that this has to be the case with a broad class of systems. So ladies and gentlemen, all this comes back to today, and all this comes back to now. And all this comes back to the unlikely combination of here in Saskatchewan. Okay? So ladies and gentlemen, I'd like to show you some videos because we've been working on these basic ideas to explore them. And we've been working on a set of tools, that will help you use this information for good use. So I'm going to show you here one aspect of these tools that I'll be showing, and I'll show a video of this in just a minute. Basically, you involve taking a time series. This is x of t. We've done this with suicide cases from LA. We've done it with measurements from our IEP phone system for people wearing it. I've done it with measles cases weekly from the UK and Wales. No, major cities in the UK, I think it was, for that one. But basically, this shows the time series, x of t. And then I show a reconstruction of state space from that time series. And what my student Amin, who created this, did was basically he created a little system by my request which allows you to highlight a span of this, and it will highlight a corresponding span and state of this reconstructed state space. So remember that basically you're creating vectors consisting of this point. The first element of the vector is this. Second is that. First coordinate of the vector, it's one way to put it, is this. Next coordinate is that. Next coordinate is that. And it's showing this in a 3-dimensional space. And so he's selecting sort of a time period and showing the corresponding thing within this reconstructed state space. And the idea here that is revolutionary, the idea here that's actually really significant, is that, about Flores-Takens' theorem, is that we can't observe, in most cases, we don't have the luxury of observing the state space of a system up there. We don't know all these hidden variables that are underlying it. Most of them are unobservable. But if we have a good time series of it, we can actually reconstruct what those underlying dynamics have got to be, at least the ones that are causally coupled to this. The ones that are affecting this enough that their information is encoded in this time series. Okay. So what's the use of this embedded space? Okay, so we can do this fancy trick, just like the Santa Cruz Collective did in the 70s or what have you. And Flores-Takens chunk. What's the use of it? Well, one is to recognize hidden structure and order behind this time series. So I've seen time series that have been measured, and you basically look at the embedded space and you see that what looks to be quite random actually has huge regularity to it. You can predict it much more easily. You can anticipate where it's going. You can see its structure is very ordered, very regular, in a way that you wouldn't have been able to from that time series. You can visually get a sense of the dimensionality, which gets down to how complicated does a model have to be to calculate. Now, I've used this over years. I think I first started this work about 10 years ago. And I've used this to shape my understanding of how much detail we need in a model, for example, okay, to adequately account for certain dynamics. You can formally estimate this dimension by running code that we've implemented for certain algorithms. And this is the key thing. This is the thing that's got my goat. Well, not my goat isn't quite the right term for it. This has got me all excited. It's like a goat is biting me. And it's got me excited. You can assess causal influences. Given two time series, you can say with great confidence if one is influencing the other. Now that is something that will probably, well, give you something to chew on at least, much like the goat. Okay. Let's talk about this notion, this latter notion of convergent cross-mapping. This is the way that in the pages of Science, back about 5 years ago, Sugihara from Scripps Institute in La Jolla laid out a method for detecting causality in complex systems. This is from Science. And Sugihara's paper here is quite interesting, but it's also practical. And basically, what he demonstrates is the efficacy of this technique across multiple types of systems and practical applications of it using time series that are no longer than dozens of time points long. It doesn't require tens of thousands or hundreds of thousands, although we have those in spades from smartphones. And he uses this to look at a variety of types of data, and notably, within associated supplemental material, he is additionally providing detailed information on exactly how they did this and a large number of different systems to which they've applied this technique. The technique basically allows you to assess the causal influence, the strength and the existence of the causal influence of one time series on another. Okay, and this causal influence is one which is shown using state space reconstruction. Okay, now my virtual box is having some trouble right now. Okay, PowerPoint is not responding. Great. I'll wait for it because I have some videos to show you that will show this more vividly than anything I can do. Okay, ladies and gentlemen. Here's a video from my student Amin. What you're going to see here is based on a reconstruction of a system. And here we have two reconstructions. So here we have what's called the shadow manifold corrected by, or reconstructed from one of the time series on the left, and a shadow manifold reconstructed from another time series on the other. Remember I said you can do embedding on it by creating for each point a vector. And the vector has the current time, point at the current time, tau time units ago, and 2 tau before that. And he's done this basically on 2 different time series, which is what this technique requires, okay? And the basic deal here is that he is showing a means of, and I'm going to back this up a little bit just so I can narrate sort of in real time with this. So here are the 2 embedded time series. This one on the left is reconstructed from one time series. Look at the value of the time series at the current point, tau time units ago, 2 tau time units ago. The one on the right Same procedure is done, but with a different time series from the same system. Think of them as two outputs from the same system. Maybe it's number of suicides, and maybe it's information about the weather. Or maybe it's a number of infectious cases and vaccinations. Or maybe it's cases of weather and infectious cases. Maybe it's number of diagnosed mental health incidents and occurrences of unemployment, over, the unemployment rate over time. Suicides and unemployment rate. If we take those time series and we look at taking them and we posit that one is affecting the other, that one that we're considering, X is affected by Y. If X is affected by Y, it should encode some information about Y. Just like if hairs are affected by lynx, having the value of X should tell us something about the value of Y. It should tell us something about the number of lynx, right? Having the value of X over time. So ladies and gentlemen, here we're reconstructing these two things. And that's where we start. We next go and we are going to find within each of these, we're going to find a point at a certain time. Notice here he's got this so that for different periods of time it will spot the appropriate value here in the time series. This is why he's dragging it back and forth, right? So it's spotting the current. Now, this is a key point here. So here, he's finding for this point in time, the corresponding value, that's the red, within this reconstructed. Because remember, each point here turns into a vector. This is the appropriate point here. And then it's showing the closest points to that vector here. And what he's doing is he's looking to those points here. If we look at the closest points to that, the closest points in this space, points where the system was at these nearby points in the state space, does it correspond to a tightly coupled thing over here? Because if it does, it's suggesting that whenever the system is at this point, the system over here is at this point within it. Okay? So this red corresponds to the red one over here at the same time. These nearby points on the manifold, on this kind of set of trajectories, corresponding to these points here, which are fairly well clustered. And what that's telling us, actually, is particularly as we consider larger number of points in the time series, is that there may be causal influence from this to that. And when I say maybe, we're not looking at it right here, how that changes with the length of the time series. But if, as the time series increases, this becomes a stronger and stronger correlation, that's the definitive mark of not statistical correlation, but causal connection. And this is what Sugihara argues within this paper in Science and within other papers that he's published also within the peer-reviewed literature. So here, what Amin has done is reconstruct these two manifolds. Using X, time series X, he's constructed this. Using the time series Y, he's constructed that. And using that, you can visually get a sense of, okay, what point within this time series corresponds to where within the time series, and how does it correspond to points over here. So here's another point, for example, and this corresponding to a more diffuse connection, set of connections here. And you can see he's laying this down and saying, okay, how does this carry over? So this is a tool for performing this convergent cross mapping, and what it's designed to yield ultimately. This is okay. We're still getting PowerPoint having problems here. I will show you a further tool. I think this is the same basic mechanism here. Yeah, so I'm actually gonna, this one is similar enough that I don't need to show that, but what I will show is this other one that was sent earlier. Here it is. This is this demonstration of the selection. So here we have a time series, and it is shown with a certain tau. This is the reconstructed state space from that, and what you'll see is that a given subset of this, or a given sequence of this, ends up corresponding to a given point here. This gives some sorts of feels about what we can learn from this reconstructed state space about features up here. The other technique, which we just saw, is designed to help us understand the convergent cross-mapping components. So these are both tools that are designed to give an understanding, an intuitive understanding about the relationship on the one hand between time series and on the other hand the state space, the reconstructed state space. With a major goal being to develop intuition about what the structure of the system has to be to explain that state space. What are the feedbacks within the system that need to be present? How much complexity needs to be in the system to reconstruct it? Looks like this is dead here, so I'm going to have to reconstruct this. So ladies and gentlemen, what we're dealing with here is a situation where we stand to gain from a small number of time series that we can reconstruct about a system, insights into the underlying drivers, the underlying processes in those systems, the underlying processes that give rise to that time series, one or more time series. And that's exactly what we're trying to model with the tools that we're learning here. It's how to model the drivers for these underlying state space, for these that underlie the observations. Okay, somehow this ended up getting totally messed up by that crash. Okay, that's not a very good thing. Pardon me for just a second. I had a nice slot. Okay, yeah, it's okay. This is distressing. Okay, ladies and gentlemen, the basic idea though is that with convergent cross-mapping, we are taking a look at how a tight cluster here turns into, whether it turns into a tight cluster here or not, how correlated these values are as the length of the time series increases. And based on whether it converges to a high value or to a moderate value, you can get actually a measurement of how tightly coupled y is in driving x. So if you, from a reconstruction of x, can get a very high correlation with the values of y, you predict values of y using these surrounding points, and then you actually test what the value of y is for the index point. It turns out that allows you to come up with a number, a correlation, which as you increase the size of the time series will tell you how tight is the coupling. Is there any coupling at all? Is y driving x? Is unemployment driving suicides, for example? Causally, not merely is it correlated. Is it driving it causally based on the underlying state space? Is weather driving the occurrence of measles among school-aged children? School closings or school the need to stay inside of school rather than outside for recess, etc. To what degree is it coupled? Here, we can reconstruct, we can get an understanding of the strength of that relationship using this method. And we have code which basically runs and arrives at those estimates. And that's exactly what Sugihara provides in the context of his article here. This is within the context of the article. He shows a defined mechanism for looking how the correlation rises with the length of the time series, looking at everything from those with small numbers, dozens of time points, to those with thousands. We've looked at this for tens of thousands of data points using our smartphone data. And basically, looking at convergence phenomena, we can identify causal relationships. Relationships that appear to show, this factor affects that. It might be proximity to smokers affecting likelihood of actually smoking, or occurrence of a person eating at certain restaurants affecting foodborne illness.
So at the same time as much more data has become available to us, we're finding through this technique that we actually need less to make much more solid assertions.
Yeah, you can actually do this with smaller amounts of data. However, the greater amounts of data help give you extra degree of confidence.
Sure.
There's no question. It can help avoid overconfidence from smaller amounts. But yes, he does show that that it works fairly well even for modest amounts of data.
So in the early stages of building a model with relatively few empirical observations,
yes,
you can then sort of get a map of the basins and the peaks and the...
That's right.
Space.
I mean, you can get a sense of the structure of the space fairly readily. I think what's not clear in my mind, I mean, just being very frank about it, one thing that's very clear is this deducing causal relationships. I think that's rock solid. I personally, having worked with state spaces, I've developed some intuition for what they tell us, particularly about how complex a model might have to be to account for certain phenomena.
Yeah.
And I think we really need a tool like we're building in my lab to help us explore the structure of that state space in a more fulsome fashion. So, because right now I do it in R in a fairly involved way, and it's just not a really tight learning loop to sort of easily change the number of dimensions I'm looking at, the value of tau, to really visualize this state space, et cetera. It's just not super easy for me, and I feel that I could learn quite a bit more likely from this reconstructed state space if I could explore it in a more fluid fashion. And that's why we're building tools like this. Yeah.
I just like to ask a question.
No, you go ahead.
Yeah.
I think my question is more like following through yours, so you go ahead.
Yeah.
So I mean, with the one or two time series, you can then you get an idea of the phase space.
Yeah.
And you can then say, well, this looks like a model with which is going to have about 3 important variables.
That's right.
10.
Exactly. Yeah.
And you can then
and use that
constructing your model. You've got
use that to help shape
what makes sense and what doesn't.
That's right. I mean, another thing is that you can make out from is how pronounced the stochastics are in driving things as opposed to other effects. But perhaps for me, the most profound element of this is just taking data that has no obvious structure to it, that looks like random walks or something. It's not really obvious that it's structured, and plugging in and seeing there's a very well-defined structure there. It's just the structure was not evident until I used this lens to look at it. And now that I saw the structure, it gives me much greater confidence about basically what dynamics I'm expecting to see from the system. It's just I wasn't looking at it with the right lens. And that's a significant, motivator for modeling, that there's some underlying regularities here, which if we could capture them would help us anticipate the dynamics of the evolution of the system, and conversely, in the context of counterfactuals, might help us capture what regularities we might expect out of that. And so that's a major goal here, is to be able to quickly visualize some aspects of time series in a structured way. And so when it's the type of data that's collected longitudinally, like the 40 and up study here at Sachs, for example, or some of our studies on, mental health distress as reported by psychiatric inpatients based on factors as they're moving about or or features associated with suicidal ideation within our social services databases, or suicide counts from certain counties. And we were looking at we used this method to look at copycat influences, possibility that suicides going forward might be coupled with suicides in the past, and we found very clear signal of causal connections. That's right, and particularly looking at sort of similar means where we actually have information. It's kind of tough, but it's drugs or cases of hangings or what have you. And these are things that we can look at using one of the key points here is, and it gets to Kim's question, in terms of amount of data that's useful. I mean, one time series, what this is saying, which is fairly revolutionary, is that one time series tells you a lot about the system, about the system as a whole. It may seem like it's just this tiny corner of the system, but just as information about hairs tells you a lot about lynxes, information about one part of the system with lots of measurements may actually be telling you quite a lot about what's going on in the rest of the system. Not all of the system, because if certain parts of the system aren't influencing the variable you are measuring, either directly or indirectly, it's not going to be telling you much about that area at all, if anything. But as long as there's a sort of causal influence directly or indirectly, it's going to tell you quite a bit. And this is a fairly, this particular Sugihara approach is a fairly, it's a quite new area for us, but it had enough potential that I decided, okay, we got to develop tools to allow us to do this. Now, Jeff alerted us as well, and I'll be with you just a sec. Jeff alerted us to an R toolbox, which already exists for doing some of this, but our goal is to have really fluid exploration, and we're doing virtual reality type visualization of this, as well as very interactive things where you can quickly change assumptions or change which data is shown in a very exploratory way that I think will support learning. So I'm not sharing this to you as this is going to be a magic bullet that you can plug in. But when we think about where things are going in this space, particularly like I talked about big data, this I think is going to be a big tool, particularly when looking at larger longitudinal data sets. But it's not just physiologic data or whatever. It's data of many different sorts. And I think it also tells us a lot about what we're trying to model. And we can compare our state space from the model with what we see through data collected through observables using the reconstructed one. We can take similar data from our model and see to what degree we're capturing some of this underlying structure. To what degree are we missing certain feedbacks, for example? To what degree are we getting sort of an underlying order behind our data because of our model that's similar to what we see in the reconstructed data from the real world. So Graham.
Yeah, fascinating. I mean, in clinical medicine, we're bedeviled by the problem of underpowered randomized trials.
Right.
To what extent are the assumptions of this, do they require that the key variables are being allowed to vary randomly with a high degree across all variables, or does this have any promise as an alternative and perhaps better powered way of looking at situations where actually some of the key variables that you wanted to establish the association with have been experimentally manipulated?
Right.
Why might this be a more powerful way of looking at some of those situations?
Yeah, I think it's a great question, and to be honest, I haven't thought about that at all. I mean, one thing that's very clear to me is that if you have a given variable, it's controlled so much that it's not allowed to vary. I mean, maybe it's people in the study, if they have any deviation from full compliance, they're let go or something like that. If the data from that is censored and not available, you're going to have limited understanding about how that variable, compliance in the world is going to play out. But the other variables that are explicitly manipulated experimentally, in a controlled way, I think there you might be able to actually get some significant insights from it. There needs to be some variation, and there needs to be some significant longitudinal component to it, where you're following not just you're not just getting a summary of from a cross section of the population, but you're actually, I think it's going to be much more powerful if you follow individual successively through multiple waves or something along those lines. But that's an extremely interesting question. I think it's one that could be explored, and I think one could use the simulation model to produce synthetic data of the sort we get from a clinical trial, holding certain things constant and not, and see the degree to which you're still and readily able to pick up some aspects of underlying dynamics. I would want to really buckle down and think about that more to give a more fulsome answer. Yeah.
Actually,
yeah, Jeff also, but yeah, your question.
My question is actually go back from the point that you have two time series.
Yes.
And because when you zoom in closely, you can actually not only identify the correlation, but causation.
Yes.
My question is more related to the fact that you definitely have to have a hypothesis in advance from which direction of the causation.
Yeah. You'll generally have some hypothesis.
And also,
yes.
Is there any confounding variable that influence both?
Yeah, so that's discussed significantly in this. There's certainly cases where you can have, X influences Y influences X and Y both reciprocally, which you can catch too here. So all of those give clear signal here.
Right.
And our experiments are very clear. When you don't have Y influencing X, you're going to get sigmas. You're going to get correlations which are poor. If Y is influencing X, you're going to get correlations which are high, which vary from very high to modest based on the strength of Y influencing X. Vice versa, and with reciprocal causality as well. They also look at cases where you have something like Y or Z influencing X and Y, and so really what you're seeing in X and Y is not Y influencing X or X influencing Y, but Z influencing both, and you can distinguish that from the cases where they influence each other.
Right, so that method is sort of allowing it to.
In fact, I think it's this figure right down here, right down there, where they exactly look at this.
Yeah.
Right? And they examine systematically the ways in which these are played out. You notice here's like a complex model with 1 bidirectionally influencing 2 and 3, etc. Versus here Z is influencing X and Y, or X just Y, or bidirectional, right? And here you are getting very clear signal from this. You'll notice that you are getting here, and this is for these different cases that you've got, and you've got 1 and 2 and 2 to 1, etc. Yeah.
So 1 to 4 is not very strong. 1 to 5 is not strong. 2 to 5.
Yeah, I think this 1 to 4 is this one here. Yeah, so it's sort of only moderate. 2 to 4, 3 to 4. Similarly, 1 to 5 here, sort of modest. And these are shown as sort of it says all other links not significant. So.
I think that kind of model is exactly what we would see normally, like in health, by socioeconomic factors.
This sort of thing.
Yes, that's right.
Exactly.
Rather than just 1-2 time series.
Yeah. That's right. And the strength of these connections give you a concrete sense of the strength of the causal influence, which again, so you can distinguish this from a case where there's no causal influence statistically. I mean, with the data produced by convergent cross-mapping, it's quite clear this is modest or low to modest causal influence, but it's still causal influence. And here, you're getting so this, incidentally, this C, this is specifically for this example too. Okay. And so you're getting very strong signals among these three, right? And then you're getting some coupling here. I agree with you. This is quite quite a common thing. These components here are related to these cross-map examples there, I believe. Yeah. In any case, you can read this, but the point is that I agree with you. You see this a lot. You see this a lot. You have factors related to dysphoria and addictions and suicide attempts and so on, and so mental health disorders, addictions, and suicide attempts. Very tightly coupled. And then you might have additional factors outside. But interestingly, there's also factors that might influence this, right? Like employment availability or service availability, right? The degree to which you have recourse to services for seeking care. And you could examine some causal influences because of that. So this is a very rapidly evolving area with us, and I'm just so grateful to Jeff and to Joanne, for some of the motivations for going into this. I think I first looked at this in November or something, and I just said, okay, we got to build software to support this, because I did a lot of it manually, and I said, okay, this is huge potential. I gotta look at this. Yeah, Joe.
Those causal relationships should hold up in counterfactual scenarios. So
that's correct.
Had a before and after type
Exactly.
Yeah. And I think that's
that
really key point.
That's the key thing. Because normally associations, are suggestive. There might be some influences, but they can be caused by a lot of confounders. They can also be caused by a lot of situations like this. They can further be ephemeral in the sense that you undertake a change, that ends up changing things, and that radically changes the observed associations. They're not, because they're not causal, they're not likely, there's no guarantee they'll persist under a different regime. Whereas if you can get stronger sense of what are the causal linkages, there you're dealing with the pathways, of influence in ways that are likely to be more persistent, or that you may identify as requiring real addressing in an intervention. So it can really inform intervention selection. But it can also help you cross-check your model's representation. To what degree have we really captured things here? So there's a lot more to learn about these techniques, but we're trying to make it, as Andrew Page says, bog simple to do these sort of analyses. So we can really, read data in and try analyzing, make it, and try to build our intuitions with respect to state space. So that's a little bit where we're at with this. As I said, something totally different from what we were doing with adding in hazard rates, but something I think it's quite exciting.
Yeah, it's extremely relevant. Yeah,
and
because that's how you actually use data to inform your model.
That's right.
Or build a model. So without this understanding, you don't really.
That's right. I think Jeff had a question.
Well, it's more a comment. Where I see this going is that you look at linking it with Simon's evolution of hierarchical control in nearly decomposable systems. I guess the real issue is we're dealing with really complex systems of systems, and therefore how do we actually chunk the system when we're just putting in all this stuff that we think we need to model?
Yeah.
The real question is, where are these tight clusters of things
That's right.
that are nearly decomposable, and then how can we understand, again, a lot of this is in systems biology, this evolution of control and semi-permeable membranes and cells, and then strategic and tactical and operational control, all the different time levels. So again, this idea of, as I say, most of that is really, as I say, in the systems biology literature, but this evolution of hierarchical control, which seems to be common.
Right. Right, and we need pathfinders. We need ways of identifying reliable indicators of causal influence that are not merely correlational. I mean, one of the things that is noted in sort of this this context is we can get cross correlation, for example, in this case, but what we're looking for is causal influence, right? And this can help us, and we can, by comparison with similar results from our dynamic models, we can identify, flaws in our dynamic models. Because remember, dynamic models are learning tools. Yep. They're tools for spotting inconsistencies that would have been latent in our head, would have been unrealized, and help us root them out. And so, to the degree that this provides another way of doing that reliably, it's a very helpful thing. So I'm very hopeful about this. Over the next few months, we're going to be advancing this by leaps and bounds, and we've got 3 separate software engineering efforts on different components of this. One more at big data, one for visualization of time series of to modest size, and one using virtual reality sort of to visualize the 3D state space in a clearer way, and to develop better intuitions for it. So we'll be adding to this, and probably in another 6 months we'll be in a position to be able to really readily offer large-scale tool use for this sort of mechanism. Yeah. So I'm really excited, and we'll get a lot of experience in the trenches pouring in. Anyway, it's 5 o'clock. Thank you very much for your attention today on a very full and diverse day. And tomorrow we'll be exploring a bunch of additional topics, including use of particle filtering, so sequential Monte Carlo methods. I'll talk a little bit about Markov chain Monte Carlo, but I'll also talk about exploring interventions, and we'll take a look at building interventions with that model in a way that will be quite rich and not require a lot of additional mechanism. Okay? Thank you very much for your attention today, and I look forward to seeing you tomorrow. Thanks. That's good comment. Thank you very much, and thanks for your patience.
Chris just emailed me.
Oh, yeah.
To ask you to respond to her message.
Okay.
She sent you a message on, what does she call that?
Oh, Google Messenger?
No, it sounded different.
Oh.
I'll look it up again. Let me
Thanks. This is great.
You let me know.